This we're going to look at the atom, and we're going to specifically look at forming electronic configurations. So you should be able to classify the first 20 elements in the periodic table based on the number of outer electrons that they have. You should be able to state Aufbau principle, Pauli exclusion principle, and Hund's rule, and how they are used to find electronic configurations. And finally, you'll be able to give electronic configurations using two methods, the Bohr method and the sublevels method. So, what is an electronic configuration? An electronic configuration shows the arrangement of electrons in atoms of an element. There's three parts to an electronic configuration. The first part is the energy level, and that will usually be a number. Then we have the sublevel or the orbital, and their letters either S, P, D, or F. And the last thing is the number of electrons, and that's usually a superscript. So electron configurations can be done in two ways. They can be done using the Bohr model, which is an easier method, or the energy sublevels method. So we're going to start with the Bohr method. So, if we look at how to form Bohr electronic configurations, if we jump straight to the answer in this slide, we can see that the Bohr model configurations only involve numbers. So, let's look at a method. Find the electronic configuration of chlorine. So, to do that, you go and find chlorine on the periodic table, and it has atomic number 17, so has 17 electrons. So you keep looking at the periodic table and you see that n equals 1 has two elements. So this means that the n equals 1 main energy level can hold 2 electrons. If we go for the n equals 2 period, we can see it has 8 elements. This means that n equals 2 energy level will hold 8 electrons. So we can see that chlorine is the 7th element in the n equals 3 period. So that means there will only be 7 electrons in the main energy level of n equals 3. So that's where we get our configuration of Cl equals 2, 8, 7. You don't have to go into as much detail in writing your answers each time. It can be shortened down like we do on this slide here. So if we go straight into the question, we can see find the Bohr electronic configuration of calcium. Calcium has an atomic number of 20. There will be 2 electrons in the first energy level, 8 electrons in the second, and 8 electrons in the third. So those 3 energy levels will be completely full. Once we get to n equals 3, we've 18 electrons already used up, so we only have 2 left. So that means that n equals 4 will have 2 electrons. So that means the Bohr electronic configuration of calcium is 2, 8, 8, 2. So if we move on to the sublevels electronic configuration, before we start it, it's important to know the order of your sublevels. So we can compare this little flowchart here with our diagram, and this flowchart is extremely important to know. So you always start with the 1s orbital, and it has 2 electrons, and this is indicated down here with the 2 arrows, one pointing up and one pointing down for the 1s orbital. Next we have the 2s, and we can see from our diagram that the 2s holds 2 electrons. Next we have the 2p. Now the 2p holds 6 electrons, but it is made up of 3 orbitals. It's the 2px, the 2py and the 2pz, each holding 2, which gives us our total of 6. Next we've got the 3s, which holds 2, the 3p, which holds 6, and similar reasonings for the 3s and the 3p. Next is very interesting. We've got 4s followed by 3d, and this is very important. If we look at our diagram, the 4s is lower in energy than the 3d, so we would always fill the 4s first, and we will see that on the next slide. So just to tie things together, we can see that the 1s comes from the energy level n equals 1, the 2s and the 2p comes from the energy level n equals 2, the 3s, the 3p and the 3d all come from the energy level n equals 3, and then the 4s comes from the main energy level n equals 4. So when doing electronic configurations using the sub-level method, there's a few rules you need to follow. The first one is AFBAO principle, and it states when building an electronic configuration of an atom in its ground state, you fill the lowest vacant energy levels first. And that's really important. So that's why we know that we will fill the 1s, then the 2s, then the 2p, then the 3s, then the 3p, then the 4s, and followed by the 3d. That's why we follow that order, because these are in order of increasing energy. The next principle that we want to look at is Pauli exclusion principle. And Pauli exclusion principle states that no more than 2 electrons can occupy an orbital, and they must have opposite spin. So in our energy level diagram that we had, you'll have seen that if we look at, let's say, the 2p, in the last slide, it had 3 circles for the 2px, the 2py, and the 2pz, but in each circle there was only 2 arrows, and they were pointing in different ways. So that means that each orbital only has 2 electrons, and the arrows pointing in the different ways indicate the opposite spin. The last rule that you need to know is Hund's rule, and Hund's rule states when there are 2 or more vacant sublevels of equal energy, the electrons occupy the sublevels singly before filling them in pairs. So if I was to do this out for you again, if we look in my 2p, I will fill them singly first. So 1, 2, 3, and then I go back to the beginning to fill in the 4th. So the arrows in the boxes indicate the direction of the spin. So the clockwise spin is the positive or the up arrow, and the anti-clockwise is the negative and the down arrow. So here's an example. Write the electronic configuration SP. SP means sublevel for the atom of calcium. So the first you find calcium on the periodic table, it's element number 20, so it has 20 electrons to be distributed over the sublevels. The first main energy level that we have is n equals 1, and it consists of the 1s orbital, and the 1s orbital can hold 2 electrons, so that means we have 1s2. Next, we move on to the n equals 2 main energy level. Now, it consists of the 2s sublevel and the 2p sublevel. The 2s can hold 2 electrons, and the 2p can hold 6, 2 in the 2px, 2 in the 2py, and the 2 in the 2pz. So that's where we get 2s2 and 2p6. Similarly, same thing for the n equals 3. So the n equals 3, we have the 3s and the 3p, with the 3s holding 2 and the 3p holding 6. Now remember, we don't go straight to the 3d because we know that the 4s is lower in energy than the 3d, so you fill the 4s orbital first, and that's where we get 4s2. So our final answer for our sublevel electronic configuration for calcium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So for these examples, what you need to remember is the order of our sublevels. So it's 1s, 2s, 2p, 3s, 3p, 4s, and 3d. And this needs to be remembered when you're doing the examples on this slide. So if we start with fluorine, we know that fluorine has 9 electrons. So we know that it's going to be 1s2, 2s2, they're going to be full, and then it's going to be 2p5. And we know that because 2 electrons will go in the 1s, 2 electrons will go in the 2s, and there is 5 electrons left out of the 9 to go into the 2p. If we take a look at silicone, Si, it has an atomic number of 14, so it has 14 electrons. So again, it'll be 1s2, 2s2, 2p6, so I've used 10 electrons so far, so the 3s will be full, 3s2, followed by 3p2. If I look at potassium, potassium has 19 electrons. So the 1s will be full, it'll have 2 electrons. The 2s will be full, it'll have 2. The 2p will be full with 6. The 3s will be full with 2. And the 3p will be full with 6. At this point, I have put in 18 electrons, so that means there is 1 electron to go in the 4s. And finally, I have sodium. Sodium has 11 electrons, so 2 electrons will go in the 1s, 2 electrons will go in the 2s, that brings me up to 4, so 6 electrons will go in the 2p, so that brings me up to 10, so I have 1 electron left and it will go in the 3s. Now, for the D block on your periodic table, there's a slight difference. So to get the electronic configuration of a D block element, write the electronic configuration of calcium and count along the row of the D block to find out the number of electrons that need to go in the D sublevel. So for example, titanium is Ca3D2. Now, that can also be written as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d2. And where I got calcium from is up as far as the 4s2. That is the calcium. So this section along here is why we just put in calcium. So if you put it in these little square brackets, we understand that this is what you mean here. There is some exceptions in the D block electronic configurations, and those exceptions are chromium and copper. And if we skip to the bottom here, sublevels that are exactly half filled or completely filled have extra stability, and that's extremely important. So if we come back up to chromium here, we would expect it to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. So we would expect the 4s to be full and the 3d to have 4 electrons in it. However, that is not what we get, because if the 3D can hold 10 electrons and there's only 4 there, but we know that sublevels that are exactly half filled have extra stability. So if we promote one of the electrons that's in the 4s to the 3D, we would end up with 4s1 and 3d5. So this would give us 2 half-filled orbitals, which would give extra stability. So the 4s and the 3d are half full, so that gives us extra stability. It's a similar situation with copper. You would expect it to be 4s2, 3d9. However, we know sublevels that are exactly half full or completely full have greater stability. So if one of these electrons from the 4s was promoted up to the 3d, you would get 4s1 and 3d10, and you would have the 4s would be half full and the 3D would be completely full, so that would give us extra stability. So those 2 exceptions are very important, along with the explanation as to why. Okay, so let's try an example to find the electronic configuration of vanadium and to draw the energy sublevel diagram. So in the top corner of the slide there, I've written up our orbital our sublevel order, and we're going to use that to find the electronic configuration. So to begin, vanadium has an atomic number of 23. Electrons will go in the 1s, 2 electrons will go in the 2s, 6 electrons will go in the 2p, 2 electrons will go in the 3s, 6 electrons will go in the 3p. If we count our electrons so far, we've got 2, 4, 10, 12, 18. So I still have 5 electrons to fill. So I will fill the 4s2, and 4s2 will be left with 3d3. So now let's do the energy sublevel diagram. So if we look, our electronic configuration is up here. So we just need to fill this into our energy sublevel diagram now. So in the 1s, we know we've 2 electrons. So put in your 2 electrons, ensuring that we've 1 arrow up and 1 arrow down to indicate the opposite spin of the electrons. The 2s has 2 electrons as well, so we fill those in. The 2p has 6 electrons, so you must remember when you're drawing an energy sublevel diagram that you fill your orbitals singly first and then doubly. 3s2, that's full. 3p6 is full, again, fill singly first. 4s2, again, that's full. And then the 3d3, you must fill it singly, so 1, 2, 3. And that is your energy sublevel diagram and electronic configuration for vanadium. So we've dealt with ions multiple times before, but just to go over it, atoms that gain electrons have a negative charge, and atoms that lose electrons have a positive charge. So let's do some electronic configurations of ions. We're going to start with chlorine 3+. So the first thing you do is find chlorine on the periodic table, and it has an atomic number of 17. So there's 17 electrons. Then what you need to do is you actually need to work out the number of electrons that are present in your ion. So we have a 3+ charge on the chlorine, so that means it's lost 3 electrons. So Cl3+ actually only has 4 electrons, and that's the key step with your ions. The first thing you need to do is figure out the number of electrons that are present in your ion. And then you can continue as normal. So it will be 1s2, 2s2, 2p6, 3s2 and 3p2. Now let's try an example that has a negative charge. So we're going to look at aluminium. And aluminium has an atomic number of 13, so it has 13 electrons. The next thing you need to do is you need to work out the number of electrons in the ion. And we've a 2- sign on our aluminium. So that shows that the aluminium has gained 2 electrons. So Al2- will have 15 electrons. And then you can proceed as normal with your electronic configuration of 1s2, 2s2, 2p6, 3s2 and 3p3. The last style of question that can come up on this topic is to identify a species when you're given the electronic configuration. So here we have the electronic configuration of 1s2, 2s2, 2p4. So we know that this ion has 8 electrons, coming from the 2 plus 2 plus 4 to give 8 electrons. The 2+ charge tells us that the ion was formed when an atom lost 2 electrons. So the atom from which this ion is formed must have 10 electrons, and that 10 is coming from the 8 electrons that are present plus the 2 electrons that are lost. And the element that has 10 electrons present in it is neon. So the electronic configuration of 1s2, 2s2, 2p6 with a 2+ charge overall comes from neon.